Today, we are plunging into the, frankly, fascinating world of secure and private function evaluations. Just imagine being able to compute something really sensitive with someone else, maybe comparing medical data or verifying credentials without either of you ever revealing your private information. It sounds a bit like science fiction, right? But it's actually very real, and it's foundational to how we might protect our most valuable digital stuff in the future.
It really is quite something. And yeah, our source material for this deep dive comes from excerpts of a seminar by Muhammad Bingol that was back on May 12, 2025. We've also got the audio discussion that went with it. Our goal here is really to pull out the core insights, the must-knows from this research. We want to give you that shortcut to understanding, the basic ideas behind secure multi-party computation, how these things called garbled circuits work their magic, and where the really cutting-edge stuff in private computation is going.
Okay, let's dive in then. So the core problem, secure function evaluation, or SFE. At its heart, it's about, what, two or more parties. They want to compute something together using their own private inputs, but crucially without showing those inputs to each other. What makes that so tricky?
Well, the trickiness really boils down to two main things. First, neither side should learn anything about the other's private stuff beyond what the final answer naturally reveals, of course. And second, you have to find the solution without needing some kind of, benevolent, all-knowing third party that both sides just happen to trust completely. That trusted third party, that's often the biggest roadblock in the real world.
Right, that makes sense. Okay, let's try and ground this with some examples because that's where you really see the impact. You could be thinking about secure voting, maybe, where you tally votes, but nobody sees the individual ballots. Or privacy-preserving biometrics like using your fingerprint to log in, but the system never actually sees your fingerprint pattern.
Exactly. Or things like private set intersection. That could be useful for, say, DNA matching in medical research, or checking against a criminal database without revealing the whole database or the person's identity if there's no match. Even things like e-auctions and bidding systems. You want the highest bid to win? Sure. But nobody wants to reveal their actual bid amount until the auction is over.
And that point about the trusted third party, sometimes it feels like you could have one, but then you hit scenarios where it's just impossible. Like the example from the seminar, the satellites.
Yeah, the satellite collision avoidance example is great for illustrating this. You've got, thousands of satellites whipping around Earth. High risk of collision.
Yeah.
They need to stay, let's say, 600 meters apart. Each one knows its own precise 3D location, its XYZ coordinates, and they need to figure out the distance between them. If it's less than 600 meters, that's an alert. Simple enough calculation. But here's the kicker, like you said. There's no trusted third party just hanging out in space that they can both securely report their positions to, and neither satellite owner, maybe their competitors, wants to reveal their exact path to the other. That's a classic SFE problem.
That satellite example really does bring it home. It just makes you think, okay, how on earth do you do that?
Yeah.
So how do you solve that kind of problem without a trusted intermediary? This brings us to multi-party computation, MPC, and specifically this idea of garbled circuits. And this wasn't just some minor idea, right? Andrew Yao won a Turing Award for this concept. That's like the Nobel Prize for computer science. So it's a pretty fundamental breakthrough. Oh, absolutely. A huge deal. The basic idea behind garbled circuits is that pretty much any function you want to compute securely, distance calculation, vote tallying, DNA matching, whatever, can be represented as a Boolean circuit, like a diagram with wires and logic gates, AND gates, OR gates, XOR gates. And in this setup, you typically have two main roles. There's the garbler, sometimes called the constructor, who sets up the scrambled circuit. And then there's the evaluator, who actually uses the scrambled circuit to get the result.
So the garbler basically takes the original problem, the function, and turns it into this kind of scrambled secret key version. What does that actually involve? Can you walk us through it a bit? Yeah, exactly. Think of the function like a complex network of light switches and wires that's our Boolean circuit. The garbler doesn't just encrypt the data flowing through, they sort of encrypt the switches and wires themselves. For every single wire in that circuit, input wires, output wires, wires connecting gates instead of a plain 0 or 1 signal, the garbler creates two unique random secret keys. One key represents 0 for that wire, the other represents 1 wire. Then, for each individual logic gate, each switch, they build a kind of encrypted truth table, so like a little locked box. And this box contains the correct output key, but encrypted, based on whichever input keys arrive at the gate. It essentially turns every single component of the computation into its own little cryptographic puzzle piece.
Okay, wow. So the Garbler constructs this incredibly intricate, scrambled puzzle. What happens though? How do the actual private inputs from both parties get fed into this thing without, giving the game away?
Right, that's the next critical piece. And it relies on another fundamental cryptographic tool, oblivious transfer, or OT. Specifically, a common version called 1 out of 2 oblivious transfer. Imagine you have a sender, let's call her Alice, and she has two messages, maybe M0 and M1. And you have a receiver, Bob, who wants only one of those messages, say M, where B is either 0 or 1, representing his choice. The goal of OT is for Bob to get his chosen message, M bin, but Alice should have no idea which one he picked, 0 or 1. And crucially, Bob should learn absolutely nothing about the other message, the one he didn't choose.
That sounds incredibly powerful, but also kind of paradoxical. How can he get one without her knowing which and without him learning about the other? Why is OT so central? I've heard it called almost magical.
It really is foundational. What's truly amazing about OT, and this blew people away, is a famous theorem by Goldreich, Macaulay, and Wigderson from back in 1987. They proved that if you have a secure way to perform oblivious transfer, you can, in theory, use it as a building block to construct any secure multi-party computation protocol for any function. Think of it like the ultimate cryptographic Lego brick. If you have enough OT bricks, you can build anything securely, secure voting, private auctions, even that satellite collision check. It shows us the absolute core requirement for this kind of computation.
Wow. Okay, so this one primitive OT is basically the universal ingredient you need. That's
Yeah.
that's genuinely mind-bending considering the complexity we're talking about. So let's connect it back directly to the garbled circuits. The garbler makes the circuit, scrambles their own inputs using those secret keys, and sends the whole package to the evaluator. But the evaluator still needs the keys corresponding to their private input bits to even start the evaluation, right? How does OT help get those keys across?
Exactly. That's precisely where OT comes in. For each bit of the evaluator's private input, they need the corresponding secret key from the garbler, either the key representing 0 for that input wire or the key representing 1, but they need to get it without telling the garbler what their input bit actually is. So they run an oblivious transfer protocol for each one of the evaluator's input bits. The garbler acts as the sender, holding the two keys for that wire, key 0, key 1. The evaluator acts as the receiver, using their actual input bit 0 or 1 as their choice B. The OT protocol ensures the evaluator gets only the key they need, key. The garbler learns nothing about B, the evaluator's input, and the evaluator learns nothing about the other key they didn't choose. It's the perfect secret handshake to distribute those initial keys.
I see. That clicks now. It lets the evaluator dip in and grab exactly the keys they need for their specific inputs, completely blind to the garbler. But you mentioned earlier protocols like Belair and Macaulay. They often relied on pretty heavy math, right? Was that a bottleneck?
It definitely was, initially. Those early OT protocols often used public key cryptography, the same kind of math that underlies things like RSA encryption or secure websites. Think of it like needing to do a complex, time-consuming mathematical proof for every single bit the evaluator needed a key for. It's very secure, but it's computationally expensive. If your circuit has thousands or millions of input bits for the evaluator, doing that many public key operations becomes incredibly slow and impractical, a huge bottleneck.
Okay, so how did they get around that? Did they find a faster way to do the OT itself?
Sort of. They developed a really clever optimization called OT extension. The basic idea is this. Instead of doing thousands of expensive public key OTs, you do just a small constant number of them, maybe 128 or 250s, regardless of how many you ultimately need. You use these initial base OTs as a kind of cryptographic seed. Then you can use much, much faster symmetric key cryptography, things like hash functions, which are super fast, to generate a massive number of additional OTs very, very efficiently. It drastically reduces the overall cost. It's like using a few very secure slow trucks to set up a network and then using incredibly fast secure drones for the bulk delivery. It made large-scale garbled circuits practical.
That sounds like a critical development for making this stuff usable. Okay, so we've covered hiding the private inputs really well with garbled circuits and OT, but what about the scenario you touched on earlier? What if it's not just the data, the ingredients that are secret, but the function itself, the recipe? Like an AI company has a breakthrough algorithm, they want clients to use it on their data, but they absolutely cannot reveal how the algorithm works. That's their secret sauce. How do you handle that? This must be where private function evaluation, PFE, comes in.
You nailed it. That's exactly the motivation for private function evaluation, or PFE. Generic SFE protocols, like the basic garbled circuits we discussed, usually assume the function, the circuit diagram itself, is known to everyone involved. It's public knowledge. But PFE is designed specifically for situations where the function, the algorithm, is private to one party, or maybe even where both parties bring a private function and private inputs to the table. Think about that inventor with a revolutionary factoring algorithm. They want to sell its use, maybe charge per calculation without ever revealing the method. And the user wants to factor their secret number without revealing it. Standard SFE can't quite manage that double-blind scenario.
Ah, okay. So PFE is about hiding the how, the actual logic, not just the what, the data going in. That's a really significant step up in privacy.
Precisely. And because it's more complex, PFE research puts a huge emphasis on efficiency. The number one priority is usually reducing the number of communication rounds, the back and forth messages. Network latency is often the killer. After minimizing rounds, the next focus is minimizing the total amount of data sent, the communication cost, because bandwidth can easily become the bottleneck before raw computing power does.
So if the function itself is secret, how do you even start to garble or hide it? That sounds way harder than just hiding input values.
It is definitely more complex. It involves a pretty sophisticated framework. Usually, the whole task of PFE gets broken down into two main phases or categories. First, there's something called circuit topology hiding, CTH. This is all about obscuring the structure of the circuit, how the gates are connected, what type of gate each one is, A and D or XOR, the whole blueprint. The goal is that someone evaluating it might learn the rough size, like the number of gates or inputs/outputs, but they can't see the internal wiring diagram or what each specific gate does. It hides the logic flow. Techniques like oblivious evaluation of mapping or oblivious extended permutation, which builds on OT, are often used here. Second, after the topology is hidden, you have private gate evaluation, PGE. This part uses techniques related to secure computation, often building on garbled circuits again, to evaluate the individual gates privately, now that their type and connections are obscured by the CTH phase. Okay, that makes sense conceptually. You hide the blueprint, CTH, and then you securely execute the hidden steps, PGE. And the sources we looked at, they mentioned significant progress here, especially on the efficiency front. Absolutely. Recent research has made huge strides. For example, there are optimizations mentioned that bring down the cost for output gates, the final result gates to just 2 encryptions, and internal gates down to 3. These build on and improve older methods. Perhaps more significantly, this line of research has led to ways to extend the fundamental garbling techniques themselves. The upshot is that now, pretty much any standard secure function evaluation SFE protocol can be transformed into a private function evaluation PFE protocol.
And the impact on efficiency, the communication costs especially, was described as pretty dramatic.
Yeah, monumental, really. The sources cited examples where circuits with something like 2 to the power of 25 gates, that's over 33 million gates. A massive circuit might have previously needed, say, tens of thousands of gigabytes of communication. Just unthinkable. But with these new PFE techniques, that can potentially be brought down to just gigabytes. That's a reduction by orders of magnitude. It's like going from needing a supercomputer storage for one run down to something you could download reasonably quickly. It makes PFE vastly more practical. Some newer approaches even use ideas like reusable templates to amortize the setup cost and make things even faster for repeated evaluations.
Okay, this is all incredibly powerful stuff, but it leads to a practical question. If oblivious transfer is this universal building block, and garbled circuits combined with OT can theoretically solve any secure computation problem, SFE or even PFE, then why aren't they just used for everything? Why do we still hear about all these other specialized MPC systems? Things specifically for, like, zero-knowledge proofs, snarks, or threshold signatures.
That's a really great question, and it hits on a core trade-off in this field: the tension between generality and efficiency. You're right, garbled circuits plus OT are Turing complete for secure computation. In theory, they can solve any computable problem securely. However, they aren't always the most efficient way to solve every specific problem.
Okay. So for something really specific, like setting up a snark-proof system or doing a threshold signature where, say, 3 out of 5 people need to sign something, there might be custom-built MPC protocols designed just for that specific mathematical structure, and those might be faster.
Precisely. Those custom protocols can often achieve much better performance, fewer rounds, less communication, faster computation, because they can exploit the unique algebraic or mathematical properties of the specific task they're designed for. They leverage shortcuts that aren't available in the general-purpose garbled circuit approach. The downside, of course, is that these specialized protocols are well specialized. They typically can't be used to solve other arbitrary problems. Garbled circuits offer that amazing universality, the power to tackle any function, even if it sometimes comes with a higher overhead cost compared to a specialized solution. It's always this balancing act.
That makes a lot of sense. It's the classic specialist versus generalist trade-off, but applied to cryptography. Well, that brings us to the end of our deep dive into secure and private function evaluations. We've gone from just hiding sensitive data to protecting the very algorithms themselves, all without needing that trusted third party. It's truly a field pushing the absolute limits of privacy and security online.
Yeah, we've seen how these core cryptographic tools, like oblivious transfer and the really ingenious design of garbled circuits, make it all possible. And the ongoing work in private function evaluation, PFE, it really promises even more sophisticated ways we can protect both our data and, increasingly, our valuable algorithms and intellectual property in this super-connected world.
So, for you listening, what really stands out from all this? Where else do you see these incredibly powerful ideas, this deep privacy and computation potentially changing things? Think beyond just, say, secure data analysis. How might this change the game for intellectual property protection? Or even how could distributed AI models collaborate or be trained without revealing their core programming or private training data? It's a huge landscape with some really profound implications to chew on.